Hi everybody, in this section we're going to start talking about JFETs and MESFETs. The acronym JFET stands for Junction Field Effect Transistor, and MESFETs stands for Metal Semiconductor Field Effect Transistor. So what are these devices? The first conception of a JFET was essentially to try to pinch off the current inside a bar of material. So imagine we have literally a bar of silicon and we fabricate 4 contacts on it. So we fabricate a source ohmic contact on one side, and a drain ohmic contact on the other. And then on the 2 opposing sides, let's put some contacts that will connect together and make our gate. Now, if we started out with N-type body of silicon, then we could put a P+ layer here and a P+ layer here. And now we've got 2 opposing junctions, and we would call this a JFET. The only difference with a MESFET in concept is that instead of making a PN junction at these 2 points, you make 2 Schottky barriers, which can be put into reverse bias. So let's look at the, conceptually, let's look at the conductivity between the source and drain as a function of the bias on the gate. Let's look at what happens in terms of the current from source to drain as a function of the voltage from source to drain. And we're going to investigate this as a function of gate bias. So for no applied gate bias, both of these depletion regions around these 2 PN junctions are very small, and so this channel is mostly open, and we get easy conductivity between the source and drain. Thus, we get high current. Now, as we start to add reverse bias to the gate reference to the body of this transistor, the depletion widths will progressively march out from these 2 contacts, and we'll see progressively less and less current until finally we can pinch off the current. So this is if we look at the individual PN junctions here, the gate bias is putting these PN junctions into reverse bias. And so pinch-off happens conceptually where the 2 depletion widths meet in the middle, and the conductivity through the depletion region is very small because the depletion region in our depletion approximation is devoid of charge carriers. So we can do some simple calculations and imagine that we have a symmetric structure where the thickness here is 2 times A from top to bottom, and either one of these is A. So the pinch-off condition and first approximation is when the depletion width coming from these PN junctions equals A. And remember, our depletion widths are functions of voltage. So in reality, this isn't the whole story. What we've just drawn is sort of for infinitesimal source-drain voltage. But if we look a little more closely at the shape, if we look a little more closely at at the shape of the depletion widths, and I'll just draw the top one for clarity. So here's our P plus region and our N here. So if we apply a large source drain voltage, we have the superposition of an electric field going in this direction, as well as the electric field in this direction from the gate. And so the contours of equipotential become slanted like this. So as especially as higher and higher source drain voltages are applied, the depletion width will distort from sort of rectangular in shape to sort of almost triangular in shape. And so if we bring in then so this is the center line here, this was the thickness A. If we imagine bringing in the depletion width from the other side too, what we see is that pinch-off sort of happens at a point first, and typically it would be on the drain side with the setup we've had here. And to fully pinch off the channel actually takes more and more gate bias as a function of source drain. However, as soon as you have one high resistance point in the channel, this is rather low resistance, so the current flowing, it will change, but not as much as the initial pinch-off. And so we have a rollover effect where the ideal transistor would have a flat current as a function of drain source voltage, but you can push more and more current through this almost pinched off region for any given, excuse me, that's the wrong one, for any given gate source voltage. So if we add more and more gate source voltage, we would get curves that would go down like this. So this would be for low, and this would be for high. So phenomenologically, the current versus voltage curves for the JFET look almost the same as those for the MOSFET. So we spent a lot of time in detail talking about MOSFETs, and many of the same characteristics happen for the JFETs also. And so we won't go into them in as much depth. Now, what's different about the MESFET? The MESFET design is typically one-sided instead of two-sided, and we can draw it here and investigate that in 1 second. So a MESFET, in terms of its physical operation, is very similar to plain old JFET that we just described. However, the details and implementation are slightly different. So MESFETs are typically made in a material that can be made semi-insulating. And silicon is not as easy to make semi-insulating as many of the 3,5s. Let's say gallium arsenide is a great example. In semi-insulating materials, the Fermi level is pinned in the middle of the band gap, especially by the addition of intentional impurities like chromium, or in the case of gallium arsenide, by manipulating a little bit of extra arsenic in the material. So this substrate is semi-insulating, and that means it's got high resistivity. Basically, it acts just like a depletion width, has very high resistance. Now, it also takes the MESFET also takes advantage of the epitaxial technology that exists for these materials like gallium arsenide. So what's done is an N-type channel or epi layer is added on top of the semi-insulating substrate, and then 2 ohmic contacts made as source and drain. And then in the middle, in the middle, a Schottky gate is added. So in the zero bias case, imagining that the depletion width here is infinitesimal, the source and drain have a very nice low resistance channel between each other, and a lot of current can flow. So again, let's look at the V source drain, I source drain, and again at no or low V gate you get a lot of current, and then at large reverse bias V gate with respect to this depletion width, you start to pinch off that that channel. So as we increase the gate bias, we'll eventually shut down this channel, and because of the semi-insulating substrate, there's actually no connection except through that either the high resistance channel region or that's been depleted, or the high resistance semi-insulating substrate. So eventually you'll get pinch off. So conceptually relating it back to the JFETs we just talked about, the MESFET structure I've drawn here would have only one, a thickness, an active region thickness of 1 times A, but the physics in terms of pinching off the channel as a depletion width moves in is exactly the same. So let's look at pinch off and just do a quick calculation of when it will happen in terms of the applied gate bias. So we have our diagram here with symmetric gates coming in from both sides on a sort of typical JFET. And remember that the p-n junction has a finite built-in voltage even with no external bias. And so this depletion width will be a certain thickness. Now, I've drawn this for the condition when there is some source and drain bias applied. So our usual equation for the depletion width is here. And then if we take the pinch-off point at the point where the depletion width coming out of either one of the 2 opposing gates here reaches the thickness A, then we can invert this equation and solve for that voltage. Now it's traditional to to lump these 2 parts together at that point and say, so if we're at this condition A equals WD, this is the internal bias, but this is the actual bias that you have to apply with an external source. And as you can see, that bias gets larger and larger if there's high doping, the N-type doping here, and also, of course, if the structure itself is very large. So this leads us into an interesting discussion about how hard or easy it is to actually pinch off a channel well. So let's imagine we're going to look in cross-section. So we're going to look from this direction, from the source to the drain, and we only have the gate contacts on the top and the bottom, let's say. So these are the two gates. And let's just kind of look at the cross-section of our channel as we add more and more gate voltage. So the channel will start pinching off like this, but it's harder and harder to control conductivity through the sides here than it is to pinch off in the middle where there's no fringing fields at all. So what if we could actually make an improved structure where we wrapped the entire channel all the way around in the gate? So then we'd have pinch off happening from all four sides at once. And the last part to pinch off would be the center. Now it's hard to make such a freestanding transistor, especially in wafer-based fabrication. So the best thing that can be done is actually to get three gates around it. And this structure, because the way it's implemented is to actually etch a freestanding fin in the wafer. So all this here is the substrate, and we've etched down from the sides here, leaving this as our channel. And then, again, we're looking along the source to drain direction here. What if we could wrap the entire thing in a very thin oxide and then apply a gate metal around it on the other outside? So this structure is known as a FinFET. And of course, PN junctions, Schottky junctions, or MOS capacitor structures can all create depletion widths that move into a semiconductor. So from the side, a FinFET might look like this, and the gate may extend over a large portion of its length, like this, leaving space for the contacts at the ends. So this structure is easier to pinch off because you have the depletion widths moving in from multiple sides simultaneously. The trade-off, though, is that the actual physical cross-section of the channel has been reduced quite a lot. And so there are design trade-offs that have to be taken into account when designing these transistors. So for digital logic applications, this kind of structure is actually currently used in the smallest transistors in Intel chips. And instead of just using a single fin, what they've done is parallelize three fins next to each other in order to increase the current carrying capacity, and called this the tri-gate structure. And now the tri here could refer both to the gates coming in from three sides on each fin, or the fact that they've added three fins. So compared to the single fin, we've got 3 times the current capacity while maintaining the same degree of channel control. And then compared to the flat topology transistors, we've greatly increased the control over the channel and reduced the leakage, which will help in power consumption quite a lot. If in the off state there's less and less current, it means that there's less and less power draw by the integrated circuit made up of these transistors. So again, that's called the tri-gate, and I believe it came out in about 2011 from Intel. So before we finish with this discussion of JFETs and MESFETs, let's take a look at some very basic equations governing the relationship between current and voltage, drain and source current and voltage, and then the transconductance, which relates the drain source current to the gate voltage. So the first equation here gives the saturation value where this starts to roll over, and this IDSS refers to the current which flows at zero applied gate voltage. Now that current flows through the channel which is bounded by the depletion widths at zero bias, or the built-in the built-in voltage induced depletion width. So that's what IDSS is. And then we have a similar expression to in MOSFETs, a squared function of the gate source voltage, which defines a parabola for a family of curves having different gate source voltages. So our increasing V gate source goes this way, and these rollover points or saturation points are going to describe a parabola. Now the transconductance here is the derivative, remember, of the current gate source versus the drain source versus the gate voltage. And so this looks slightly different, but has a very similar form to what we've seen in MOSFETs. So although the actual details of operation are very different, many of the external characteristics of these transistors are very similar to what we encountered in MOSFETs. And so we won't go into any more detail here in this class.